4. Digital twin for human. A digital twin of a person, hereafter referred to as a human digital twin, plays a quite important role in the DTC vision, which aims to provide a wide scope of value through interaction with other digital twins in a virtual society. In this section, we propose a definition and structure for a human digital twin to provide a reference model. Human digital twins will be used not only for monitoring the corresponding individual's current states but also for predicting their future states, substituting their activities, and conducting simulations of various future societies. Therefore, a human digital twin should not just be a collection of information, such as photographs, biological signals, and action logs, but also have processes to perform human-like behaviors. Human behaviors are affected by various mental/internal factors such as thoughts, memories, and emotions, but we currently have no rational model that can describe all of the corresponding structures and mechanisms. Therefore, to build a human digital twin, it is necessary to design such mental/internal elements according to reasonable assumptions. We believe that the existence of such mental/internal elements, which can be assumed as the consciousness of a digital twin in a sense, is a unique and important characteristic of human digital twins in DTC. We assume that the physical aspects of human digital twins, such as their appearance and superficial movements, will conform to the definition and structure of digital twins of physical objects as described in 3. Digital twin for physical object. Therefore, when considering only these superficial/physical aspects, for example, monitoring a human's posture or heart rate or simulating a new hairstyle or golf swing, it is unnecessary to follow the definition for a human digital twin described in this section. Rather, it is sufficient to follow the definition for a physical object. On the other hand, if mental/internal factors such as thoughts, memories, intentions, and emotions are important even for a non-human entity, we recommend referring to this section. 4:1. Hypothetical model of human digital twin as described in the hypothetical structure of digital twins in 2.2. Hypothetical general digital twin model. A human digital twin consists of 3 kinds of information: physical, intelligent, and social. Moreover, each kind of information consists of 3 types of entities: data, process and interface. For a human digital twin, the data includes not only the instantaneous state of the corresponding individual but also the structure and characteristics that model that individual. The process entails the mechanisms and algorithms to drive the human digital twin. Thus, the process generates autonomous reactions on the basis of data in response to real or virtual world stimuli obtained through the interface. Basically, a reaction involves updating a human digital twin's data, and interaction is achieved by observing such updated information from other entities. In this subsection, we describe the typical elements for each kind of information. Note that the elements presented here are just examples and do not cover all potential elements. Furthermore, we do not require that human digital twins include all of these elements. 4.1.1. Physical information for human digital twin. We define the physical information as observable or measurable. Hence, observed external or superficial information such as appearance can be considered part of the physical information. The physical information may also include internal but measurable data, such as data about muscles, and blood vessels, and biometric information such as the body temperature, heart rate, genome, and epigenome. Note that the types of physical information for a human digital twin are basically the same as those for a physical object, as described in 3:1. Reference model of a digital twin. Although the representation format or granularity of the information could be different. To simulate human behaviors and visualize a human digital twin in a virtual society, physical information may also be described in terms of rational structures and mechanisms, that is, the data of physical information could be expressed as a set of structural models and their parameters. For example, The shape of a human digital twin can be expressed as a set consisting of a three-dimensional reference postured model with skeleton information and joint angles, 26, 27. The facial action coding system, FACS, is another example, in which human facial expressions can be represented as combinations of fundamental facial movements called action units, 28. We also assume that the process for physical information can be descriptive and explainable by using mathematical models based on common principles, such as the laws of physics. For example, a human walking action can be described by using a kinematic parameterization, 29. 412. Intelligent information for a human digital twin. We propose to define internal psychological information, such as affects, emotions, memories, thoughts, and intentions, as the intelligent information for a human digital twin. This kind of information is processed in the human brain and cannot be acquired directly by using sensors or other means. The data of intelligent information consists of the psychological or mental status of the corresponding person in the real world. We assume that the data is expressed by using representational models that can be directly understood by humans, rather than by physical signals or quantities of chemical substances, which would need to be interpreted or translated by experts. Note, however, that such physical signals and chemical quantities can still be considered as physical information for a human digital twin. The process of intelligent information corresponds to the internal mechanisms of human psychological and mental behaviors, and it thus determines the psychological and mental status of a digital twin in a simulation. Note that the process of the intelligent information generates reactions not only for intelligent information but also for physical information. Various representations and mechanisms have been proposed for intelligent information not only in computer science but also in other fields including psychology and neuroscience. To the best of our knowledge, there is no complete, unified definition. For example, roughly speaking, emotions have at least two different representations, the discrete categorical model and the continuous dimensional model, and no one can judge which is better. As for the internal mechanisms, many studies have modeled the human decision-making process in the context of agent-based, social, simulation, 30. The most historical model is a simple production rules system, but a neurologically inspired model has been studied as a more persuasive model. We assume that a wide variety of representations and models might be used and could coexist in the DTC platform. We do not require that one human digital twin must have all kinds of representations and models, but we should define a common interface to allow interaction between human digital twins based on different models, in order to achieve interoperability of digital twins constructed for different purposes. 413. Social information for a human digital twin. The social information for a human digital twin is defined as various kinds of information that accumulate in human relationships. It includes, for example, a person's name, gender, occupation, values, common knowledge, rights, and culture. In contrast to intelligent information, social information is meaningful only when considering interactions with others. Social information may be referred to by the process for intelligent information and may affect its output. We assume that at least two types of social information should be considered. One is information that can be shared with others at a certain moment. This type of information includes the common knowledge, values, and historical views that are shared by an ethnic group, nation, or similar kind of group. The other is information originating from spatiotemporal continuity. This type of information represents the characteristics within a group that result from shared history. For example, it may include parent-child relationships, the support of a fan for a sport team, and other attachments. 4-2. Digitalization of human This section discusses how to build a human digital twin as described in the previous section. Humans are quite complex and most aspects of them have not been elucidated, but we will describe the methodology that we currently envision to digitalize real-world individuals. 421. Related works and studies. There have been many works and studies on building digital models of humans in various research fields to date. Modeling of human physical information has been conducted in the field of computer graphics since the 1960s. A pilot model was presented as the first digital animation model of a human in 1964-31. While more precise human digital representations are still being explored, various technologies have also been developed to scan real humans. In the computer vision community, by using multiple cameras and lights, precise surface geometry, i.e., shape, and reflectance information, can be obtained, resulting in a photorealistic 3D model that looks exactly like the scanned person. 32. Note that a 3D model built by scanning in this way is generally a fixed, static model, but by applying the computer graphics technologies called rigging and skinning, it is possible to generate a parameterized variable model to which different postures and facial expressions can be applied. Technologies for direct acquisition of such parameters for generating postures and facial expressions from humans in the real world are also being actively researched and developed. Among recent AI-related technologies, human pose estimation is one of the most basic research topics. For example, MIT's OpenPose is one of the most popular technologies, showing the potential for digitalization of human motion in the wild through deep learning technology. 33. As for intelligent information, as mentioned in the previous section, there is no universal representation. However, emotion is a typical kind of intelligent information, and many technologies have been developed for human emotion estimation. Some of these technologies estimate human emotion from information such as facial expressions and voices that can be observed by the 5 human senses. 34, while other technologies use biological signals such as brain activities and heart rates. 35. Although these technologies can achieve quite high performance in terms of accuracy for labels based on third-person judgment, it is still difficult to judge whether they actually estimate a person's subjective emotions. Moreover, the existing technologies only estimate around 4 to 8 kinds of emotions, called basic emotions, and it is still difficult to estimate the more complex emotions that humans have. Mental/internal processes have also been studied in many research areas, including philosophy, psychology, neuroscience, and computer science. The research is ongoing, and we cannot yet define a universal, rational model even for a part of the intelligence process. For example, the human decision-making process is considered one of the most basic human processes and is thus being actively studied, especially in the area of agent-based modeling. As reviewed in 30, a wide variety of models have been proposed for different purposes. One of the most traditional models is production rule systems. 36. A production rule system models the human decision-making process with a set of simple behavioral if-then rules. Although humans are not as simple as that, this kind of modeling might be useful for analyzing simple tasks performed by humans and implementing them in a machine or robot. In contrast, cognitive models were proposed to achieve more realistic social simulation based on knowledge in cognitive science. PEX is one of the simplest cognitive models. 37 and has a component-oriented architecture. It includes physics, emotion, cognition, and social status components in its internal layer in order to model physical, emotional, cognitive, and social influences. It seems possible to model a minimum level of human-like mental/internal processes, but the rational modeling methods for each component have not been clarified. Lastly, psychologically and neurologically inspired models are among the most complex models, but they seem to have a relatively rational structure because the structural properties of the human brain are considered in their design. Most models in this category are designed to implement human cognitive functions and learning mechanisms. Although their main purposes include understanding specific human behaviors and the brain system, their architectures are designed to be simple, and other aspects such as emotions and social elements are rarely considered. For example, ACT-R, which is one of the most famous models in this category, was developed to model human behavior in psychological experiments, and the core scheme is based on a production system. 38. SAW has a relatively complex memory module and leaning architecture, but it has no effect-related module. 39, even though emotion is one of humans' fundamental functions. This might be because there was no rational structure or mechanism in the fields of neuroscience and cognitive science. 422. DTC digitalization process for human. To obtain a human digital twin, it is necessary to digitalize each person individually. As defined in 411. Physical information for human digital twin. The physical information for a human digital twin is observable or measurable. It is thus possible to digitalize such real-world information by using sensor devices and other methods that are appropriate for the target information. Because the physical information of humans in the real world changes constantly, though it might be sometimes quite subtle, digitalization, i.e., sampling, should be performed at the necessary intervals for a DTC application. In contrast, the intelligent information for a human digital twin is not directly observable or measurable. Thus, the data for intelligent information is estimated from the measured physical information. We refer to this estimation process as psychological decoding. 2. Perform psychological decoding. It is necessary to define a representation model for the target intelligent information in advance. For example, we should define whether to use a discrete categorical model or a continuous dimensional model as a representational model for emotions, as well as the kinds of emotional categories or dimensions that will be used. Any method can be adopted for psychological decoding as long as it fulfills the performance requirements of the target DTC application. Deep learning-based technology can provide highly accurate decoding results. However, such methods are constructed using a huge amount of data from different people and thus might need to be tuned with individual information. The digitalization of the process is one of the most important and difficult issues in creating human digital twins. Basically, we assume that human digital twins are modeled on collected data for physical and intelligent information. However, human digital twins will be used not only to reproduce the past activities but also to predict future status and simulate unknown situations. Therefore, it might not be appropriate to just model the process as one that reproduces the inputs and outputs of collected data, as in the recent AI approach. Instead, We think it is necessary to model the process, so as to explain the collected data while defining a reasonable internal structure or mechanism, rather than relying on a black box. As for the definition a reasonable internal structure/mechanism, we think that reference to knowledge in physiology and psychology is one of the best approaches for creating human digital twins. We assume that one of the typical applications for human digital twins in the DTC vision will be to perform various tasks on behalf of the corresponding real individual. 40. For such applications, it is important that the human digital twin should be recognizable as the corresponding individual not only by himself/herself but also by the people involved in a task. We define this capability via requirements for identity and personality in human digital twins. And we consider it essential to fulfill both requirements. We also expect that it will be quite difficult to achieve such individualities only from objective information obtained by sensing. Therefore, some applications might require subjective training or modification of a human digital twin by the corresponding individual. Human digital twins will live in a virtual society even though they are connected to humans in the real world. Therefore, unlike conventional agent models that are completely separated from the real world, a human digital twin should have a mechanism to reflect real-world information at appropriate times. The data could be reflected by being overwritten with real-world information. On the other hand, because the process cannot be directly obtained, we should implement some update strategies. For example, the process could be tuned at a predetermined time according to the data stored after a previous update. Another example is a kind of online update method in which the process would be updated according to errors between predicted data using the current process and observed data, similarly to predictive coding in the human brain. This would provide a kind of mechanism that a human digital twin could grow according to the experiences of the corresponding individual in the real world. There remains an open issue of how to define and implement a growth mechanism of corresponding real human, according to the experiences of the human digital twin in the virtual society. 4-3. Requirements for a human digital twin, preliminary draft as described in our DTC white paper. We aim to use human digital twins to extend human capabilities in the real world, compensate for decision-making, and make simulation-based predictions. We think, therefore, that a human digital twin in the DTC vision should fulfill the following requirements. Note that the content in this section is under discussion and might be updated by considering the nature of humans from both the humanities and engineering perspectives. 4.3.1. Connection to corresponding human in real world. This condition is the same as that for a physical object. A digital twin of a person shall have a connection to the corresponding human. However, unlike for physical objects, there may be ethical issues in changing or controlling the physical and psychological status of a human in the real world by manipulating the corresponding digital twin. This requirement means, therefore, that at least the data of a digital twin shall be updated on the basis of the status of the corresponding human in the real world. 4.3.2. Identity. A human digital twin shall be recognized by the corresponding human as a digital version of himself/herself. This requirement implies that a digital twin of a person shall not be created without that person's approval. 4.3.3. Personality. A human digital twin shall be recognized as the digital version of the corresponding human by most of the human's acquaintances? This requirement is a condition for achieving valid simulation of various interactions in a virtual society. 434. Autonomy. The autonomy of a digital twin is defined as the ability for it to decide its own behavior in response to inputs/stimuli. A human digital twin shall react validly to any inputs/stimuli. Accordingly, a human digital twin shall be not terminated even in unexpected situations. 435. Ego. A digital twin shall not execute, fire/start, any processes without approval by the corresponding human. 436. Uniqueness. There shall be only one digital twin for an individual in the digital twin layer. This means that a human digital twin and the corresponding real human will have a one-to-one relationship. 437. Discriminability. A human digital twin and the corresponding real human shall be distinguishable in not only their appearances, but also their behaviors and consequences.